to know this on site. You need to know that this is this is the exponential model, right? And you should have, Anthony, you would have seen this yesterday?
Yeah, I did see that.
So this is the exponential model, and your final equation looks something like P equals C e to the kt. Depending on what your variables are, things work differently, right? But the P stands for not necessarily the principal. It's like your population, right? Like if it was the number of whatever.
Yeah.
The principal is what the C value is, right? This is like your initial amount.
Yep.
And T is normally time, and K is your constant, like your constant of proportionality, or it's your growth rate constant. And so it is totally okay and strongly encouraged that if you see this differential equation, dp dt equals k times p, to jump straight to the exponential version. We've done it so many times, you just know. Is everybody okay?
Mm-hmm.
And then there's the new kid on the block. Logistic. Logistic growth. And the way that that works, we've got dp dt. Okay. The rate of change of your population is equal to, what's the equation? You just have to know it on site.
K
times P
times
C 1 minus
L minus
L minus P. I hear the one, I know where you're getting it from. Okay? Now, all the players, right? So this dp dt equals K times P times L minus P. It's a more sophisticated differential equation to solve. And we are not going to waste our time solving it again and again and again. We are absolutely not going to do that. That's not the point here. I do want to make sure that we know all the right things. So K, it's going to be your like growth rate constant. They're going to give it to you in some way in the problem. So it's the growth rate constant. And the P stands for your population. So like population at time t. Like yesterday we had the grizzly bears and how they were growing on the island, right? That was our population at any time t. L, this is a special one. It's your limiting capacity, or some people call it your limiting population. Others call it your carrying population. That means like it's the most number of things you can support on your island, your enclosed environment. But I think L makes more sense because then you're going to think of this as limiting population. Okay, L minus P. It's not the current. If P is your population, your current population, and L is your limiting population, then L minus P is how much else I could carry. Like I called it yesterday the available population, but it's like this is your limiting population, this is the most you can support, this is how many you have. Basically this is saying how many more could I have. So this is like your available population. And C is going to be another constant. Constant of integration. Well, here's the good news. Really good news for you all. If you have a differential equation in that form, but it has to be that form, exactly that form, any small change, doomed. Then I'll tell you that the final equation looks like this. P of t, your population, the numerator is L, your limiting population. And then it's going to be 1 plus this constant c. You're not going to know the constant c at the beginning. You're going to have to do a little bit of work for this. And then it was e to the negative k, whatever that rate over there is, times L, your limiting population, times t. And if you look at the example, I know we were going fast at the end of the day yesterday, that's exactly what happened. What did we have yesterday as our opening problem? It was like dp dt, was it like 0.001?
Yeah.
Times p times, was it 100? 100 minus p? So the L was this guy over here. The K, this guy over here. We had to do some work to figure out what the c was. We're always going to have to do some work. But if I remember this correctly, our final equation was p equals 100 over
1 plus 9.
1 plus 9. That's where we had to do a little bit of work. And then it was e, and then the exponent, it's this guy times this guy. So 0.001 times 100 is negative 0.1 t. And the way we checked it, we said if t is equal to 0 at time 0, this guy here is 1, times 9 plus 1 is 10, 100 divided by 10 is 10, and we started with 10 grizzly bears. The other end that you check is what happens as t approaches infinity. This part here goes to 0. 9 times 0 plus 1 is 1, 100 divided by 1 is 100. It all works because we get that limiting capacity. How are we doing? Mostly okay? Okay. Anthony, you're at a disadvantage right now. I understand. Okay. But really, what I want you to get to is if you see this form here, if you see this not exponential model, but this is your logistic model, I want you have my permission to jump straight to L over 1 plus C e to the negative k LT. Don't derive it, just know that this is the end result. Okay, we derived it yesterday, we're never going to do it. Never. Okay? All right, now, here's what's going to happen. Depending on the textbook that you pick up, and Anthony, I think this is what you were seeing over here. Some textbooks write their logistic growth formula differently than I do. They've got the K, good. They've got the P, good. 1 minus P over L, not so good. Looks and feels a little bit different, right? So if you did this though, what if I factored out 1 over L? Which might seem strange to factor out 1 over L. But to factor out just means divide. 1 divided by 1 over L is L. Minus P over L, factor out the 1 over L. Is P. And then I've got K times P times this 1 over L. Your L is a constant that you're going to know in the beginning. The K is a constant, so I can rewrite this as K over L times P times L minus P. The difference, though, is that now your constant in front involves your limiting capacity. Everything's going to work all the same way. And you're going to play around with this one a little bit more tomorrow. Mr. Link has offered to stay here with you guys. You'll have my solutions. You'll have another example problem. Lots of practice. Okay? All right, so let's wrap up the notes, and then maybe if all goes well, we'll look at a couple of quick multiple choice questions. All right, we've got a slope field here. And specifically, this is the slope field that goes along with the differential equation at the top. Is everybody convinced that it's logistic growth? If it's the form. Heck, it's all the same variables and all the right things. If you look really closely in the slope field, I think you can probably see there's 2 horizontal lines hiding in there. Can you see them?
I see one. The other one's kind of slight.
Okay, where's one of them?
I don't know if I can point anything over there. But right here.
Okay, so like right up here, there's one. Anybody see the other one? It's like right down here at y equals 0. You've got a horizontal line over here, meaning you have like a solution curve here at y equals 0, and then you've got another one over here at y equals L. These are solutions to the differential equation. And we'll talk about it in just a little bit. What if I pick an initial condition that's up here? So what I'm saying is the y value that I'm starting with is less than L, but it's greater than 0. This is my initial condition, the 10 grizzly bears on the island. Well, what happens when I draw my solution curve?
It approaches the y equals 1.
right? What's going to happen is it's going to approach that line. It does increase, but then we know something happens. Like it increases and it crosses. There's an asymptote, right? It increases and then it levels out. That's one of your solution curves. This is that S-shaped curve that you guys have talked about in apes. What we're saying here is if I pick a number as my starting condition that is greater than 0, but not quite the limiting capacity, well, what's going to happen to the population? My population is going to grow. It's going to grow towards that limiting capacity. Will it ever reach it?
No.
It doesn't actually reach it. Does it ever pass it?
No.
Does it ever like approach and go back down?
No.
No. What's going to happen if you're thinking about like your grizzly bears on this little island, the number of grizzly bears is going to increase, and then it's going to like level off. It's going to plateau. You're at that carried capacity. Brian.
For like the grizzly bear example, it would never like have 100.
It's going to get really close. I mean, in a real world situation, we're going to have to embrace rounding. We're going to say 99.886 grizzly bears. Well, that's 100 grizzly bears. Or it's like a grizzly bear and one that looks like this. Yeah.
Are we ever going to have to face a scenario where it's like process and comes back down?
No, because that wouldn't be logistic growth. Great question. Well, what else could happen with the initial condition?
You could start talking.
Okay, so if I take another case, so let's look at another case. But the way I'm gonna, so this is like case 1. Case 2, that initial condition is greater than L. Well, what happens? That initial condition is greater than my carrying capacity. My carrying capacity is 100 grizzly bears, but I drop 200 onto the island. What happens? They have to die out. There's not enough food, there's not enough space, there's not enough lady bears. However you want to describe it, there's not going to be enough bears, and so the population decreases towards that 100, but flattens out. So I'd say in case 1, if I wanted to describe this, I would say like the solution increases towards L. In this case over here, if y naught is greater than L, then my solution curve decreases towards L. Decreases towards L. Anything else that could happen? We've got an initial condition over here, and we increase towards L. An initial condition up here, we decrease towards L. Any other options?
Could stay at
Starts at 100.
Could it start at 100?
Yes.
If you start at 100, if you start right here, so we're saying y naught equals L, well, what happens to the grizzly bear population?
Stay the same.
It's going to stay at 100 grizzly bears. That does not mean I just made 100 immortal grizzly bears. What does it really mean?
Some die, some are born.
Some die, some are born, but mathematically we're saying it's happening at the same rate, so I balance. Right? So I'm going to be, my solution curve is going to be like right over here. So I would say that this guy over here stays constant. What else could happen? There's 2 more cases I want us to consider.
Less than 0.
Less than 0. What? First of all, I think we probably have to lose the grizzly bear situation now. You have dropped onto the island -4 grizzly bears.
So
Not to be confused with 4 angry grizzly bears.
4 dead bears.
4 grizzly bears with an attitude problem. No, that's not why they're negative. It doesn't really make sense to have a negative number of grizzly bears. But look at the slope field. What does the slope field tell you to do? If you follow those little tangent lines, what are they doing? You're decreasing. Decreasing. Look at your tangent lines. Are we ever increasing?
No.
All you're doing is decreasing. So in this case, we decrease towards -infinity. One more case.
Could you explain how that makes sense?
In terms of grizzly bears, it does not. In terms of a slope field, it does. If we remove like real world constraints, like I can't have a negative number of grizzly bears, What I'm saying is if I pick a point below the line y equals 0, the slope fields tell me I'm going to be decreasing towards negative infinity. There's one more case. What if you start with y equals 0? I think this one works in both situations. You go to this island and you drop off no grizzly bears. What does the solution curve tell you? There's no grizzly bears. Okay? So what you have is another stable solution. What you would say is stays constant at L equals 0. Those are your 5 different cases. I want to add on a little bit more vocabulary here. This guy over here is called, y equals L is called a stable equilibrium. And this guy down here is your unstable equilibrium. I don't want you to get too bogged down with the vocabulary here, but equilibrium just means, like in chemistry, in science, equilibrium means balance, right? I'm balanced. So I'm calling y equals L a stable equilibrium because what we're really implying is as I get closer and closer and closer to this horizontal line, y equals L, what happens?
The population either decreases or increases.
One more time.
The population either increases,
Decreases,
or
or increases, but specifically how does it decrease or increase? It decreases or increases in a way that you're getting closer
to the carrying capacity.
to that carrying capacity. This is considered down here an unstable equilibrium because if I pick points around here, if I pick an initial condition around 0, well, what happens up here? My population grows away from 0, or my population decreases away from 0. Big picture, we okay?
Yeah.
Don't get bogged down with the vocabulary. The grizzly bears work well, except over here. The grizzly bears will work for you. All right. Why is there a number? I knew you were going to ask that. And I knew it was you that was going to ask that. In the back of my head for the last 45 seconds, I've been like, why was there a number 6? Why was there a number 6? Why was there a number 6? Here's why there was a number 6. It's not a 5th case. This is just a thing that I want you to know.
Always problem.
Here's a thing that I want you to know. When it comes to logistic growth, we are always growing. Always growing. Except this case where we're always decreasing, but in this case down here we're always growing. The growth happens fastest when you are halfway between 0 and your limiting capacity. So wherever this point is over here, this is when growth happens fastest. And if I look at what's happening, the way I drew my graph, before I hit this point, my function is increasing. After I pass this point, my function is increasing. There is a difference, though, before this point and after this point.
How much they grow by? It's
Close. It's a change in the concavity of the graph.
Oh.
If you were to graph your solution curve, this part over here is going to be concave up. Wow. Can't even spell the word up. And this part over here is going to be concave down. Which, if that means that if at this magic point over here, I'm growing the fastest, my concavity just changed from concave up to concave down, I think we have another word for this point.
Point of inflection.
It's a point of inflection. Okay, so this guy here is your point of inflection. And I have looked through like 2 decades worth of AP questions, and they only ever ask, what is the y value at the point of inflection? And what's the y value at this point of inflection? It happens halfway between these two. So I'm never going to ask you, or I probably won't ask you what the x value is. The y value is half your carrying capacity. Yeah.
If they were to ask X, how would we answer that if it's just like, how would you feel?
Okay. I've looked at 2 decades worth of AP exams, okay? They're gonna ask you at what Y value. Meaning, how many teddy bears? Grizzly bears. How many grizzly bears are on the island when the population is growing fastest? 50. 50. And I think if you just think about it conceptually, you've got this like sweet spot between how many grizzly bears you have on the island and how many grizzly bears you could still have on the island. And because the growth is directly proportional to the product, right? I want these two to be equal so that this guy is as big as possible and this guy is as big as possible so that the product, which is the growth rate, is as big as possible. For those of you that just need something to memorize that it is halfway between the zero and the limiting capacity. Everybody okay? Brian?
Will there always be an asymptote at y equals 0?
There will always be an asymptote at y equals 0. Think about the grizzly bears. Grizzly bear population on the decline. What's going to happen? Extinction level event. Sad for the panda. Now they're Man, I got it all over the place with the bears.
Caught him honey.
All right, so I've got 2 multiple choice questions that I hope that we can do together, and then that'll set you guys up for success on the homework and quality time with Mr. Link, who apparently has like a little like sticker chart. His goal is to teach all the math courses by the end of the year. Yeah, it's coming to a 7th grade math class near you soon. All right.
7th, 8th, and 10th. That's what I need.
7th, 8th, and 10th. All right. The population of bears grows according to the differential equation dp dt equals 0.02p minus 0.0002p squared, where p is the number of bears and t is measured in years. What's the limit as t approaches infinity? I want this to be like a 1 minute or less question. Is this exponential?
The original function, or?
Is this an exponential growth rate?
Yeah.
No.
Logistic growth?
That was
Yes.
Factor out.
If you look at it really closely,
Because I don't see the L.
you don't see the L,
Factor out.
right? The key is they're tricking you. Do a little factoring. Use legal algebra stuff here. So legal algebra stuff I could be thinking about right now is factor. What would I factor?
0.02p.
Okay, I can like factor out 2/100ths p. Now if I factor out 2/100ths p, 2/100ths p factored out of 2/100ths p is
1.
1 minus,
Something.
oh yeah, love it. Oh dear.
0.001.
001. Hey, James Bond.
007.
If you're not 100% sure, factoring means divide. 1, 2, 3, 2p squared divided by 1, oops, just 1, right? 0.02p, the p's cancel. 2 divided by 2 is 1, cancel out a 0. This should be 0.001p. If you need to do a little calculator action, that's fine too, I won't judge. Does this fit our model? No, it doesn't.
Oh, because it doesn't have the K. Wait, no.
But we do have the
0.2.
K.
Yeah.
We have the K,
Okay.
we have the P. This doesn't look immediately like our model. The reason that it doesn't look immediately like our model is we normally have L here, L minus P. Not L minus some number times P. We have L minus P. Factor out the 0.001. So if instead I said dp dt equals 0.002p, so 0.02 divided by 0.0002 is going to be 1,000 minus p. And now in that form, I hope the logistic part is clearer. dp dt equals some constant times my population times the available population. What's the limiting capacity here? The limiting capacity, the most number of bears I can support is 1,000. Right, this guy over here is your limiting capacity. That's not the answer. The question says, where P is the number of bears and T is measured in years, what's the limit as T approaches infinity?
So we just do the equation over here.
Okay, you could go through and do this.
The
You could go
shortcut,
through and do that.
the L over 1 plus C.
Okay, so what's L?
You said 1,000.
1,000 divided by 1 plus what's C?
I don't know.
Don't actually know. Let's keep going. E to the, what comes next?
Okay, so.
It's the negative of this guy times this guy. So it's going to be negative 0. What is that? 0.2t. That's your population equation. You guys are about to want to smack your heads. What's the limit as t approaches infinity? Let t approach infinity. What's going to happen? If t approaches infinity, e to the negative 0.2t has to get closer to 0 times c, the constant that we weren't able to figure out. 0 plus 1. 1,000 divided by 1 is 1,000. It shouldn't be a surprise that the limit as t approaches infinity is 1,000, because what does the 1,000 represent?
The carrying capacity.
It's the carrying capacity, it's the limiting capacity, it's the greatest number of bears you can support. You're going to approach 1,000. So, look at that.
Did you forget?
I could be off by a decimal.
Yeah.
Yeah, you can go for your calculator if you need to. Is that one? 0.02 divided by 0.0002.
Oh, it's 100.
Yeah, 1, 2, 3, 4 times. 1, 2, 3, 4 times. That would be 100. Bummer! Bummer! Thank goodness Mr. Link's going to take care of you guys tomorrow. So it's going to be 100, which means that this guy's going to be 100, which means that this guy over here is going to be 100, which means that this guy over here is going to be 100.
Yeah,
Can we edit the video so that Lucio doesn't see that? I don't need to hear that from him tomorrow.
Oh, but you won either way.
Okay, would you guys have all picked 100 right in the beginning
Yeah. I don't know.
if we had actually done the math right over here to get the 100?
Yeah.
Maybe.
Maybe. Okay, when is the bear population growing fastest?
50. Oh,
When's that bear population growing the fastest? What number of bears would cause this population to grow the fastest? It has to be 50. It's always half the limiting capacity. Just know it. All right, let's try the next one. Let's see if we can do a better job here. Couldn't do a worse job. Oh, not bears this time. It's wolves. It's going to be harder. Just a difference.
No, no,
Just gonna close it.
Take this guy here and rewrite it. Alright. So 0.01 p squared, 1/100th p squared. Factor out the 1/100th p. 3 divided by 1/100th has to be 300 minus p. If you get here, I hope the rest of this is really easy. Look at the differential equation. What do we know? Take anything from anybody. What do you know for sure? 300 is what?
Carrying capacity.
300 is the carrying capacity. Anything else you know for sure?
Is 0.0.
Okay, this is your K value. If I asked you to build the equation, you could do that. You could build the equation, except we need an initial condition to figure out the value of c. Which of these statements is true? Is it true that the limit as t approaches infinity of p of t is 300? Think about what this means, right? All they're asking you is the carrying capacity of this island, or whatever it is 300 wolves. Is that true?
Yes.
That's what the L represents. The growth rate of the wolf population is greatest at p equals 150.
Yes.
That's halfway. Good. If p is greater than 300, the population of wolves is increasing.
No.
Brian, why not?
It should be decreasing.
Decreasing, because what happens if I have more than 300 wolves?
You have limited space, so like.
I have limited space. My carrying capacity is 300, so this has to be a false statement. If the question had said, if my population is less than 300,
Then it would be.
then it would be true, because then I would grow, as long as I'm between 0 and 300. None of these questions are going to require you to derive the logistic growth formula. It is okay to go straight to the equation and play around with it. Okay? Tonight for homework, I want you guys to finish off the multiple choice. And there's 2 free response questions on the back. They look really heavy. They're not. They really shouldn't be. Mr. Link's going to share the solutions with you guys tomorrow. I'm not going to pick this up for a grade. Ooh, although the one that you guys did last night for homework, I am going to pick up. Steven Spielberg, we can shut this off. Just leave it in the middle.